Good morning. Today we're going to be looking at energy, specifically potential energy. So you can think of potential energy as stored energy. Um, there's two types. Kinetic, you can see in this image, kinetic energy, which is down here, and it has the image of this person on a swing. And kinetic energy is the energy of motion. So as you're in motion, that's kinetic energy being used. And you can see this person on the swing is actively swinging, so that's actively using kinetic energy. The opposite of that is potential energy, which is really what we're focusing on. With potential energy, it's stored. So I have this car at the top of this hill. Now it's taken some time and energy to get that car up to the top of the hill. Now it's sitting there, but it has the potential to do work or to release energy. And that's because gravity could pull it down the hill. So once that car starts to roll and starts moving down the hill, then it would have kinetic energy. But while it's sitting there, it's just potential. Batteries that aren't in use are like potential energy. They have the potential to do some work. But if they're not being used, then they're not doing it. So let's look at another image here. Since we're talking about chemistry and molecules and chemicals and things like that, you should be able to recall from the last unit we talked about octane. Octane is the gas that you are burning in your car, among other things. Now, when we talk about chemical potential energy, so it's still energy that's stored, it's potential energy. Since it's chemical, however, it's stored in the bonds between atoms. And these lines right here are the bonds. So there's a bond everywhere you see a line between atoms. So between the carbon and carbon, or between the hydrogen and carbon. All of those bonds are potential energy. It's a certain amount of energy that could be released if those atoms are no longer bound together. That bond energy can be released and used to do some kind of work. With octane, if this is a molecule of octane, we start burning it using combustion. It's the oxygen that helps break those bonds apart and really get to that energy that's in those bonds. So in the molecule that they're looking at in the next video, ATP, there's a couple areas that have high energy bonds. So the energy is stored in this bond right here. There's also high energy bonds here and also over here. So that energy is sitting there and it can be released when we break apart this molecule. That's what we're going to be talking about, the potential energy stored in chemicals. All right, thanks.
Hi, it's Mr. Anderson, and in this video I'm going to talk about adenosine triphosphate, otherwise known as ATP. ATP is usually shown with this yellow starburst behind it, and that's because it contains energy. In fact, it's the energy coinage of all life on our planet. And most of you probably know that, but you might not know the structure of ATP. And so let's begin with the adenine. Adenine is a purine, and it's a nitrogenous base. That means that the black is going to be carbon, but the blue is going to be nitrogen. Where have we seen nitrogenous bases? Remember, that's going to be the rungs found on the inside of DNA. We also have a ribose sugar, and then we're going to have not one phosphate group. Phosphate is phosphorus surrounded by oxygen, but we're going to have 3 phosphate groups. And so let's start with the adenine and the ribose. They're attached together and they form a chemical called adenosine. If we add a phosphate to that, we have AMP, or adenosine monophosphate. If we were to add another phosphate to that, we've now got adenosine diphosphate, or ADP. But if we add that third phosphate, we now have ATP, or adenosine triphosphate. Now these last phosphates are important. In fact, I like to think of the bond between these last two phosphates like a spring. As we attach that last phosphate on, we're storing energy, and so there's potential energy in that bond. There's also going to be potential energy in this bond right here as well. And so when we release that phosphate, we can release a little bit of energy. And so let's look at that. And so what is ATP? Here it is again. So we've got our adenine, our ribose sugar, and then we have our 3 phosphates. But you can think of it like a recharged battery. It's a battery that's charged up and has a certain amount of potential energy. In fact, if we were to take ATP, which would just look like salt if you were to have it in a solid form, and we were to add it to water, it would all hydrolyze. In other words, it would all break down into ADP. And so let's look at what's going on here. So if this is water, that water will break this last phosphate group. In other words, we're going to add an OH on one side and H on the other side. Remember, we call that hydrolysis or breaking with water, and we create ADP. Now we have just 2 phosphates here. Well, what happens to that third phosphate? It's released. And so lots of times when you're dealing with ATP, you're going to see this P with a subscript of I. What does that stand for? That's this phosphate group that's been given off. And since there was a certain amount of potential energy in this bond, when it's released, that phosphate has a certain amount of potential energy as well. So in other words, if we were to let ATP just sit in water, it would all eventually hydrolyze and it would all become ADP, and we'd have these loose phosphates. That's going to be like a battery that's lost its charge. And so what do we do in life? Well, in life, we're going to tap some energy. And so we could do that in respiration by breaking down glucose, or in photosynthesis by taking in energy from the sun. And we're going to attach that phosphate group again. And that's called a dehydration reaction. And so when we attach the phosphate, we now make ATP. When we break it, then we're going to release energy. And so let's start